Okay, welcome back. This is a continuation of lecture 10 or something like that. In this class, yesterday, we did what, Jordy, do you remember?
We did second derivatives.
We talked about second derivatives, check. we talked about the jerk. We definitely, the main thing that we did with much associated rambling was we came up with the derivative, we derived the formula for the derivative of e to the x, and then we went over this really hard double parabola problem, yeah? Alright, good. Then there was a little bit more homework due today. We may or may not go over any of those problems, but we're not going to right this moment, because we have a bold and incredible thing to do.
The thing we were going to do last class?
This thing. Tell me everything that we now currently know how to take the derivative of. This is our list of functions that we have tamed. It's a pretty short list, actually.
So we know the squares of exponents.
X squared.
Exponents, basically.
Exponents, basically. Okay, yeah. I think what she's trying to say is power functions, like anything of the form x to the n. Is that what you're saying?
Yeah.
Yeah.
We know cosine and sine.
I know cosine. I know sine.
E to the x.
E to the x. Eleanor?
A function plus a function.
Yeah, sums of arbitrary functions. So now it's like I'm giving you sort of a recursive definition, right? I know all of these, but I also know for any two of these, I now can take the derivative. I can take the derivative of like e to the x plus sine x, for example. Yes?
Polynomials.
Polynomials in general, yeah, because that's kind of like fits in the same. Well, okay. I'll just write well. I think what I'll actually do is I'll just observe that not only do I know the sum of two functions, but I can also take recursively. I know how to take the derivative of the constant times any function appearing previously on the list, and thus these two together with this one give me that actually I know how to take the derivative of all polynomials, and also like polynomials plus like sine, like okay, whatever. It's pretty good. The problem is there are a lot more functions out there. Lots of functions. And one thing which, for example, just boggles my mind that I have no concept of how to take the derivative of is our friend x squared sine x, for example. Is that our friend? No. Like once we probably talked about that function back in pre-calc C. This is a function which doesn't seem too hard. I know how to take the derivative of x squared, and I know how to take the derivative of sine x. But I don't particularly know how to take the derivative of x squared sine x, or do I? Ankit?
Can you just multiply the derivatives of each together? Does that work?
That would be really great, wouldn't it? In fact, strategic laziness leads us to conjecture that the derivative of the product is just the product of the derivatives. Because, I don't know, the limit of a sum was the sum of the limits, the limit of the product was the product of the limits, the derivative of the sum was the sum of the derivatives. Okay, and it would be pretty awesome if it was just like that. Okay, so true or false, the derivative of f of x, g of x is just f prime of x times g prime of x. Alright, what you are now going to do is engage in quote unquote real math. I will release you for 30 seconds to meditate upon this supposed proposition and to determine whether it is true or false. Jordy, how do you determine if a proposition is false?
By assuming the antecedent.
Yeah, there's like a fancy word that's very important.
One counterexample.
Yeah, all I need is a single counterexample, right? And so actually, that's like the easy one, right? If you give me a false statement and ask me if you wanted to determine whether this statement is true or false, I'm hoping it's false. Because if it's false, all you do is come up with this one example in which it doesn't work. Wait, hands down. And if it's true, then that's hard. Because if it's true, I have to prove it, right? So that sounds hard. Okay, so go, please. No. Think amongst yourselves. Try to come up with a counterexample to this theorem. And yeah, I guess hint, it is false. So you should be able to come up with one. All right. Someone got something? Vegeta, what do you got?
So if you set f at x to x squared, and if you set g of x to x, and then initially, let's say you multiply them together, like x squared times x is x cubed, and if you derivative of that, you get 3x squared. But if you were to do them each separately, you get 2x times 1, and that just equals 2x.
Yeah. You did it really fast. But yeah, if I let f be x squared, I let g be x, she says maybe perhaps to find a new function h, which is just the product of those two functions. If we do that, then h of x is x cubed, I guess, right? And then, this is what you said, right? You were talking really fast. The derivative of h would then be 3x squared, but according to our formula, the derivative of h should be f prime of x times g prime of x, but the derivative of f is 2x, and the derivative of g is x, so that predicts that it would be 2x squared. So almost, but like, it doesn't work. Yeah. Anyone want to give me a different example? There's like lots of, whatever, yeah.
Let's say f of x is x and g of x is 1.
Yeah, how about just like x times 1, right? What is the derivative of the x times 1 function?
1.
1, not 1 times 0, which would be 0, right? Okay, this just definitely does not work. All right, so, uh-oh. That means that this is hard. We have to do something. Yeah?
You made a mistake there. The derivative
Really?
of x is not x, it's 1.
What happened? Oh, this is what, oh yeah, you're right, I did make a mistake.
Oh no.
Okay, this is a mistake. Thank you, Arlo. Apparently one mistake and you're just kicked off calculus teacher island or whatever. All right. So now I have to now I have to figure out what's going on. I don't know how to do this. I have to now suddenly be smart. Yeah. What should we do?
Maybe we could pretend that we didn't do that and start trying to prove that it's true, and then see what we do prove. If we start with the definition like we would if we were trying to prove that it's true.
Okay, can I erase this temporarily? Because I think I like this idea. I think what he's saying is just go, right? I mean,
I mean, it might be good to think about it first, but it's
maybe. Sometimes yes, sometimes no. Should we think about it first? I don't know. Let's take a vote. Should we try to think first, or should we just try to start and see what happens?
Just start.
All right. So let's just start and see what happens. What is the so let's define a new function h to be f of x times g of x.
Can we call it k because there are h's?
It's a very good idea. Let's call the function k. Thank you. And let the k function be the f of x times g of x function. And then oh, by the way, some people, if you're fancy, you write this as like this, you know, like the f times g function taking input x. So you might see that sometimes. Great. Let's assume that f is a function which I know how to differentiate, and g is a function which I know how to differentiate. And now we're just going to figure out what k prime of x is. So what is it? The first step is always the easy step. It's just tell me what the definition of the derivative is.
Of k of f of x times g of x, or f of x plus h.
Whoa, what's happening?
K of x plus h.
Yeah, it's just k of x plus h.
Minus k of x.
Okay, yeah, that was supposed to be the easy step, just mindlessly regurgitating the formula in general for the derivative of the function k. Okay, but now what is, I guess, what is k? Let's just get rid of k now, whatever. What is k of x plus h?
G f of x plus h times g of x plus h.
Minus f of x G of X.
You agree? I have no idea what's going on right now. Do you have any idea? Yeah, I changed my mind. I think we should do some thinking. Let's do some thinking. Can you move the camera and stuff? Because we're going to think over here. So we need to do some thinking. And if we're going to do some thinking, it could be hard. So perhaps we should just like meditate deeply on all things, like what is even a derivative? What are we trying to do? What's going on? What does it mean to multiply two functions? What does it mean to multiply two numbers? Like, I just have no, I need to take everything down to scratch. Someone like to volunteer. Sam.
You're multiplying two functions is, like, for any point, for any x, you take f of x and g of x. Wait, I'm not really sure.
And you multiply the outputs. Yeah, okay, good.
Yeah.
That's a contribution. So he's reminding us that when you multiply two functions, you're simply multiplying their outputs. All right, fine. Gabe?
Multiplying is like finding the area of a rectangle where, with the sides or the numbers. So it's sort of like making one, stretching that line out by a certain number.
Yeah. Gabe is a deep man who thinks about the geometric significance of all of his arithmetic operations, and I encourage you to do the same. As we've talked about that multiple times in this class. Even I feel like this has come up. Yeah, when you multiply two things, one way in order to visualize that, and I think that visualizing what's going on is like the way to understand what's going on. We can think of this as multiplication, says Gabe, as kind of finding the area of a rectangle whose side lengths are these numbers. And this is probably the way to teach multiplication to someone who's struggling with it, like a fifth grader or whatever. Okay, well, you know, if 3 times 5 really means the area of a rectangle whose side length is 3 and 5, then I guess the product of two functions could be interpreted as the area of a rectangle whose side length is these two functions. How do you feel about that? I feel okay about that. In fact, let's even just take off the this and this. Okay, so what? Does anyone have an example of what it means to multiply? Can you think of a time when you'd want to multiply two functions? You got something?
Like when you multiply like x squared or x sine 1 over x.
No, I was thinking more like a word problem.
Oh.
I had an example, but I didn't bother looking at it before class, so I can't think of it right now. Yes?
One function models like for a factory production of some product per employee, and another function models like the number of employees you'll have over time.
Yeah, how did you come up with it? This is like the exact example I came up with. Yeah, you have some factory. Whoa. So you have some factory.
Oh, because you gave the example before, maybe.
Maybe I did.
Matrices, remember?
Yeah.
This is basically like matrices, except for not.
A lot of things going on here right now. I'm having like a weird I am gay moment. Yeah, I gave a presentation at a conference to a whole bunch of math teachers back in November, and one of the things I did was to present them with essentially all of the proofs of this class that are happening in basically this month and next month, like February and March, in 1 hour, 50 minutes even after I got done with my rambling. So one of the proofs I did was this one, and the example I gave to motivate the discussion was basically this exact example, that you have some kind of factory, and your factory is producing some product, and you have really like two functions, whoa. You have two functions which are, you have two functions, one of which is telling you, I guess it's like the, no, okay, say it again, I forgot my own example. One is like the
production per person, per employee, and one is the number of employees over time. Because like technology
per employee. Yeah, right. Okay, so F is like the number of widgets produced per employee. So number of widgets per employee, and the G is the number of employees. Okay, this is awesome. This was my exact example. It's coming back to me now. And now we have to come up with an idea in which these things would actually vary over time. Well, it seems like that could be true, right? This is the efficiency of your workers. Perhaps it's true that everyone comes in the morning and they're like really tired, and thus they're working pretty crappily in the morning. And then a little bit later on, they kind of wake up and they have some coffee break at 10. Then suddenly there's like a big push after lunch, kind of drowsy again. Towards the end of the day, start slacking off. Perhaps there's a night crew that is, you're in some weird third world country where there's like limited electricity late in the night, and so your efficiency goes down. Can you guys imagine that the rate at which an employee can produce a widget might vary over time? Do you agree?
Yes.
All right, it is also possible that the number of employees you have working at the factory varies over time, so you could have some like flex schedule situation where some people come really early in the morning and other people like me, I would show up to work at noon if I was allowed and work till 8. Some people like to work in the middle of the night. So, the product of these two functions would be what? Number of widgets produced, I guess like per hour. I guess it's like some other per hour going on here, right? Because this is really like number of widgets produced per hour per employee or something like that, right? So the product of these two functions would thus be the number, it would be the rate at which you are producing widgets, right? The company overall. Okay, I love this example. Let's kind of come up with the derivative of this function. So how do you come up with the derivative of a rectangle? What does that even mean? Well, we have to let the rectangle move. So now the rectangle is going to move. Before we even do that, what I have to introduce you to is a model of a function in which you, so take some function like f of x equals x squared, all right? Here's one thing that we never, ever, ever do, except we're going to do it now and then never again, which is represent this function as a line which is moving over time. All right. Now, why don't I do that is because we live in a three-dimensional world, and thus our surfaces are two-dimensional. And thus it is really simple for me to make a graph of this function because I have 2 dimensions to work with, and thus I model the inputs versus the outputs. Good so far? All right, now it would be silly of me to employ a only one-dimensional model for this function because it's just a waste of a dimension. But I could do so. And what does a one-dimensional model of this function look like? Well, here's like a line. This is getting really weird. Here's a line, and on this line I will have a segment which changes length over time. So at time 0, it's not very much of a line segment. And then at time 1, it's like that long. And then at time 2, it's like that long. And then at time 3, or what? That's supposed to be 4. And then that's supposed to be 9. Are you with me? So can you envision this segment just growing over time? And so you're watching, this is like a little whatever, like animated GIF or whatever of this function. That's one way to represent this function. You start the clock at time t equals -5, and the line is quite long, and then it gets shorter, and then it gets bigger again. Cool? Okay. Now we're going to do that with both functions at once. So hit the start button, and now let this animation happen. This g function is getting longer with time, and the f function is getting longer with time. Do you guys all see it? And so in fact, if we let these two functions change, what we're going to have is a rectangle which is growing and changing and growing and changing. Everybody with me? All right. Now, asking for the derivative, thus, of the product of two functions is asking for the rate at which the rectangle is gaining area. Right? If the meaning of the product is the area of the rectangle, then that's the question I need to ask. All right. So at what rate is this rectangle gaining area? Well, anytime you take the derivative of a function, what you're really doing is you're saying, at that exact moment, how fast is the function changing? And so it's kind of like you take a sort of a stopwatch, right? If you want to know how fast someone is moving at a given second, one thing you could do is you could do what we talked about like way back in the first derivative day with the stopwatch. Actually, that was the first day of this class, I believe, right? Sometime. Right? If you want to know how fast something is moving, you kind of like take your stopwatch and you sort of hit start-stop as fast as you possibly can, right? And if you hit start-stop as fast as you possibly can and you measure where the object was and where the object was later, then you can divide by the amount of time that elapsed, and that's roughly speaking the derivative. All right, so I'm going to do that same thing now. I have this rectangle which is growing and changing. I'm going to hit start-stop, and I'm going to see what happens to the rectangle. All right, well, let's just say that the rectangle gets a little bit bigger. And let's call that little bit that the rectangle gets bigger, delta G. And let's call the little bit that F gets bigger, let's call that delta F. Now, are delta F and delta G the same? Not necessarily. What determines the size of delta G? However much G changed. In other words, the derivative. Yeah, that is the derivative of G, right? The derivative of a function tells me how fast the function's changing. So delta G is determined, how much G changes is determined by whatever the derivative of G is. Okay, so the derivative of G seems very much relevant. Do you agree? And the derivative of F tells me how fast F is changing, so the derivative of F is relevant. All right, and what I have now is this new big rectangle, and thus says that, okay, so thus what is the derivative, graphically, what is the derivative of the product of these two functions? Pretty much, but some would say it in just words, like based on the picture. Oh.
The like bottom rectangle, right rectangle, and then bottom right thingy.
Yeah, right. It's like the new stuff that was added, right?
Okay.
This is FG. This is how much function I had. And if I hit start stop on my stopwatch and see by how much the function changes, the answer is going to change by a tiny bit. Okay, so this tiny bit, this amount, this excess rectangle, this is how much bigger my rectangle got over that infinitely small amount of time. Is everybody with me? Hopefully, yes? Okay, yes. So, well, let's count it. How much did the rectangle get big over that time? Well, I think I can count this. How big is this rectangle? Yeah, this is G times delta F. How big is this rectangle?
Delta F, delta G.
This is F delta G, and this one is
Delta F.
delta F delta G. Okay, so claim, this is my claim based on just common sense. This is pretty similar to what Newton did, that the change in FG, the change in the FG function, which I'm going to loosely associate with the derivative, right? This is the amount that the FG function changes over some infinitesimal amount of time, is, according to my picture, F times delta G plus G times delta F plus delta F delta G. Do you believe it? All right, now comes a semi-wishy-washy discussion in which I will argue, actually I'm not going to argue, I'm just going to appeal to your intuition, which you may or may not have, that this is like, I hope you've been getting all of this, if not I'm going to cry. Are you?
You've been getting it.
Good. If not, then I claim that delta F delta G is like negligible. Negligible. In other words, delta G is some infinitesimally small quantity. Delta F is some infinitesimally small quantity. When this is like super wishy-washy, but do you feel that this is correct? If I multiply a significant quantity like F by a very, very large, by an infinitely small quantity, I get something which is kind of significant. And again here, if I multiply a normal number by an infinitesimally small quantity, I get something which sounds like it's important. But if I multiply an infinitesimally small thing by another infinitesimally small thing, says Newton, that's just like negligible. All right, if you like it, great. If not, not. Here is, in fact, the solution to this entire problem. And if this were a lame calculus class, this would be my entire proof of the product rule. That the product, the derivative of the product of two functions is the one function times the derivative of the other plus the other function times the derivative of the other. And Gabe, this feels right for our factory example, right? Because the rate at which the efficiency of the entire factory is changing seems to depend on all four of these things, right? Because certainly it's true. Suppose that the efficiency of the workers was staying roughly constant, but the number of employees streaming into the factory at that hour was increasing quite rapidly. Would that have an overall effect on the efficiency of the factory? I say yes, right? That's delta G. So the derivative of G seems relevant to the overall change in the efficiency of the factory. But if and on the other hand, the number of the efficiency is also mattering, right? if the efficiency of the average worker at a given time is very, very, very low, then even if there are lots of employees streaming into the factory at that moment, the overall efficiency of the factory is not going to change much. This is pretty complicated. Similarly, the rate at which the efficiency of the factory is per employee is relevant, but as is the number of employees. I might have said that wrong. If the number of employees in the factory is really small, then even if they're really, really efficient, it's not going to change. So all four of these numbers are relevant in some kind of way. Do you guys feel like that was right? Okay. I think it's time to do math. Gabe, quick comment?
We've had like some functions before that have like weird curvy things that you're like, we're going to explain this in calculus. Like, I don't know. There's some.
Okay, moving on. Okay, moving on.
But
Gabe, I love you. Time to do the practical. All right. So, look. At this point, I feel so smart. I feel like I understand things on a deep level. There's pictures happening, areas happening, word problems are happening. Yes, I own a factory now, apparently.
Like, how is delta G equal to the derivative?
It's not exactly. Okay, so if you like this, good. If you didn't like this, here comes the non-wishy-washy version. Are you ready? The non-wishy-washy version is very similar to the wishy-washy version. A picture will now be created in order for us to think about this intelligently. And the picture is going to be almost the exact same picture, okay? But now, doing it properly. And so now I will draw a big rectangle. And I will label this f of x, and I will label this g of x. And x is some arbitrary point on these two functions. And now I will increase f by a little bit. I will increment to time h. If I increment to time h, then what is the length of the new side of the rectangle? Someone said it. Yeah, this is just f of x plus h now. Cool, cool? Okay, and now I'll do the same thing over here. I will model that my new rectangle is going to have dimensions f of x plus h, g of x plus h. And now I will close up the rectangle. By the way, let's go back to the thing we did just to the left over there, which is the definition of the derivative. Can you do whatever you need to do to keep this entire thing in frame? Like if that involves pulling the camera back or zooming out. It's all good?
Yeah.
Right. So, does anyone notice anything about this? What the relationship between this picture and my definition of the derivatives? Yeah, everyone.
It's the big rectangle minus this.
Yeah, look at my numerator. My numerator is literally big rectangle minus small rectangle, right? Does everyone see this? Okay, that suggests that I should try to figure out what those three rectangles are, and that's exactly what I'm going to do right now. Because what is this little piece right here then? This little piece is f of x plus h minus f of x, agreed? This little piece over here is g of x plus h minus g of x. And now, please insert into the three boxes their areas.
Is there some geometry thing that says that if you like
Wait,
draw like
we're just doing this now. Sorry, Gabe. Just doing this now. Okay. You got what I got? All right. So, just like Eleanor and others observed, what we have done is we formally are in the process of deriving the formula for the derivative of the product of two functions. When we got stuck, we decided to do thinking. And that thinking has led us to model this numerator as the new boxes which were added in this new operation, right? And so now, this suggests exactly what I should do now to continue with this limit. What do I do? just replace, right? This numerator just is the sum of these three boxes. It just is, right? f of x plus h, g of x plus h is the big box, and f of x, g of x is the small box. And so, like, I know exactly what to do now. I'm going to write, in place of this numerator, all of those. It is g of x, f of x plus h minus f of x, plus the other rectangle, plus this other one. Over h. Whoa. Alright, and in case you're worried that I'm leaning on geometry too heavily, I'm not. Right? I'm using the geometry as inspiration, but the proof is still like tight. Right? I'm not trying to like pull a fast one on you or anything. If you look at this, if you were to take this numerator, if you like love algebra and sphere geometry, if you were to take this numerator and multiply it all out, I promise you, you will get this, right? I mean, if you can almost kind of do it in your head, right? G, it's like g times f of x plus h, but then that dies like over here. So do you guys kind of appreciate what I'm saying? This, I have replaced this numerator with this numerator. The geometry was there simply as inspiration. They are, in fact, algebraically like the exact same thing. Naming something, he's nodding. You're supposed to nod. That way people know, yeah, good. All right. So now it's like everything's great, right? How do I finish this off? Yeah.
Well, and you can
Just give me like 5 words.
Split it up.
Split it up. Yeah, do that. Go. Split this up into 3 limits. Each limit representing one of the 3 rectangles. By the way, this proof is so much better than the crap that they do in our textbook. What they do in our textbook is embarrassing. They just start the proof and then they just say like, now we will perform an algebraic manipulation. And they just tell you to like, if we just like, and they just tell you to like, add this quantity and subtract this quantity, and then things magically work out. Jordy, it's terrible. And textbooks sometimes do this in like a little